Hello everyone, welcome back to this online class. Today I want us to look at the method of separation of variables as used in solving partial differential equations. And in particular, we are asked to solve the one-dimensional heat conduction equation given by partial u partial t is equals to alpha times partial squared u with respect to x twice. And this equation is defined between x 0 less than x less than L and the time t greater than 0. We're also given the boundary conditions that at x is equals to 0, the solution is 0, and at the other end, the solution is also 0. And the initial condition, when time is equals to 0, our solution is f of x, where f is an arbitrary function. So remember, the alpha here, this alpha is called thermal diffusivity. Is the thermal diffusivity. So using this method of separation of variables, we are going to say let our solution be, so say let u of xt. You see, in our equation, the independent variables are x and t. So, and the dependent variable is u. So u depends on x and t. That's why we are saying u of xt is equals to x capital times t capital, where the x capital is a function of x and the t is a function of t only. So if this is our solution, then we can also find the corresponding partial derivative. So you can say that this implies that partial u with respect to t, you keep x constant and differentiate t dt with respect to t. And so this can be written as x t prime. Also, second derivative of u with respect to x twice, that now you keep t constant, differentiate x, so t is constant. We are differentiating x twice, d squared x, dx squared. So this you can also write as t times x double prime. So remember, the prime in the partial u partial t is derivative with respect to t, and the other double prime is derivatives with respect to x twice. Now we substitute into the PDE. What will be our PDE upon substitution? So our equation will now be xt prime is equals to alpha times t x double prime. And now this is separable. This is separable ODE. So I want to separate the variables. So we divide. Let's divide through by alpha times x times t, alpha xt. What are we going to get upon dividing that equation by alpha times x times t? So this will give us, remember it is x t prime over alpha xt is equals to alpha t times x double prime over alpha xt. And so we can simplify this one. You see the x will cancel with the x, so we have t prime over alpha t is equals to alpha will cancel, the t will also cancel out. So we have x double prime, excuse me, over x. Now look at the left-hand side. This is purely a function of t only. This is a function of t only. And the right-hand side of this equation is a function of x only. And we are saying these two should be equal. A function of t should be equal to a function of x. For that to be true, then each side must be equal to a constant k. K is a real constant, a real constant. Remember k, when we talk of a real constant, this is what I mean. Negative infinity less than k less than positive. K belongs to the set of real numbers. So, and you see this, you can divide into three parts. If I draw the real number line, this side and this other side, and we have 0, there is negative infinity this side, and then here we have positive infinity. So k can either be 0, or k can be a value greater than 0 this side, or k can be a value less than. So there are three cases to consider depending on the value of k. Is it less than 0? Is it 0? Or is it greater than 0? So I'm going to call this equation, let us call it star. And now we are going to consider three cases. Consider three cases depending on the value of k. Now the first one, case 1, let's start with the negative, when k is negative. So case 1 is the case where k is less than 0. So I want us to put k is equals to negative alpha squared, where alpha, not alpha, that should be lambda, where lambda belongs to the set of real numbers excluding 0. So lambda is a non-zero real number. That should be number. Non-zero real number. So non-zero, this can be written as lambda belongs to the set of real numbers, but we exclude the set containing 0. That's how we can write it. So that means lambda is a non-zero real number. So if that is the case, then equation star becomes, so that equation star now becomes t prime over alpha t is equals to x double prime over x, which is equals to negative lambda squared. And from here, we can get this a system of what it is. We can get t prime over alpha t is equals to negative lambda squared and x double prime over x is equals to negative lambda squared. So there are two equations. Let's solve them. This is a set of ODEs. These two is a set of ODEs. So this will be our first equation, and this one is our second equation. Let's solve the first one from equation 1. Equation 1, we have, if I cross multiply, I'll talk of t prime is equals to negative alpha times lambda squared t, which you can also write as t prime plus alpha lambda squared t is equals to 0. So if I let d to be equal to derivative with respect to t, I'll get this. I'll get now d operating on t plus alpha lambda squared t is equals to 0, of which t is common, so we can write this as d plus alpha lambda squared operating on t should give us 0. This is homogeneous PDE. And so the auxiliary equation is d plus alpha lambda squared is equals to 0, and the root is, there's only one root, d1, just one root, d is equals to negative alpha lambda squared. And this root is a real root, just one. So how do we write our solution corresponding to t? So therefore, our t, which is a function of the small t, should now be equal to an arbitrary constant c1 times exponential negative alpha lambda squared t. That's the solution corresponding to t. Let's solve the second equation, equation Roman 2. So equation Roman 2 will have x double prime over x is equals to negative lambda squared, which you can write as x double prime is equals to negative lambda squared times x, which you can also write as x double prime plus lambda squared x is equals to 0. So again, we write this in terms of the d operator. So we let d be equal to derivative with respect to x, so that d squared will now be second derivative with respect to x twice. So now we need to write that equation in terms of the d operator. So our equation can now be written as, can write, or it will now be d squared operating on x plus lambda squared x is equals to 0. And so x is common, so this can be written as d squared plus lambda squared. The whole of this should operate on x to give us 0. Again, this is homogeneous ODE of the second order with constant coefficients. Auxiliary equation. Our auxiliary equation is that d squared plus lambda squared is equals to 0. So what are the roots? Make d the subject. D squared is negative lambda squared. So when you take the square root, you are going to get d. Because there are two roots, 1 and 2, will be the square root of negative lambda squared, which is the same as 0 plus or minus iota times lambda. Iota is the square root of negative 1. So we have, these are complex conjugate roots. Complex conjugates. So in this case where the roots are complex conjugates, how do we write our solution corresponding to the x capital? It will be exponential 0x times, call it C2, cosine of lambda x plus C3 sine of lambda x. And you know, anything raised to 0 is 1. So this you could write as x is equals to C2 cos lambda x plus C3 sine lambda x. So where C2 and C3 are arbitrary constants. Now we know x and we know t. We can now be able to find our solution u of xt, because we started by saying let u of xt be equal to x times t. So this is our solution. We multiply the two to get our general solution. So let me go down. Hence, u of xt will now be equal to x times t, which we know our x to be C2 cosine of lambda x plus C3 sine of lambda x times the other one was C1 exponential negative alpha lambda squared t. That's what we had. And this can be simplified because if I multiply the constant C1 and C2, I can get another constant, call it A. So let me start by writing the exponential. This is A times cosine of lambda x, that should be lambda, cosine of lambda x plus b sine of lambda x times exponential negative alpha lambda squared t. What we are calling A is simply C1 times C2. And what I'm calling B is equals to C1 times C3. They are arbitrary constants. So those are arbitrary constants. Now, this is our general solution. We need to find the values of those arbitrary constants. So we have three conditions to apply. Let's start by applying the boundary conditions. So apply the boundary conditions. The first one, we are told u of 0t is equals to 0. So this means I need to put x is equals to 0 here in this equation. Remember here we had u of xt being equal to that. So put x is equals to 0 in this equation so that you get the result is equals to 0. So 0 is equals to, remember cosine of 0 is 1. So it will be a cos 0 plus b sine 0 exponential negative alpha lambda squared t. And you know sine of 0 is 0, so this will vanish. And cosine of 0 here, they should be equal to 1. Cosine of 0 is 1. So what do we have? We simply have a times exponential negative alpha lambda squared t should be equal to 0. But remember, in the method of separation of variables, our task is to find a solution that is non-trivial. A non-trivial solution, a solution that has physical significance. So for non-trivial solution, for a non-trivial solution, it is only a that can be equal to 0. Remember, if you say exponential negative alpha times lambda squared t is equals to 0. Then it means when we substitute it here, we are going to get u of x is equals to 0, which is a trivial solution. So for non-trivial solution, a must be equal to 0. So therefore, when you put a is equals to 0 in this equation, we are going to get u of xt is equals to, now it is b exponential negative alpha lambda squared t times sine lambda x. I have substituted a is equals to 0 in this equation to get this one, the one I've written down. There's another boundary condition that we need to apply. We are told u of lt is also equal to 0. So this means that we put x is equals to L so that you get u is equals to 0. So with this substitution, you're going to get 0 is equals to b exponential negative alpha lambda squared t times sine of lambda L. Again, if you want, remember here b can be equal to 0, or this exponential function can be equal to 0, or the sine of lambda L can be equal to 0. But our interest is a non-trivial solution. Which one will give us a non-trivial solution? Automatically, b cannot be 0, because if I say b is 0, it means u will be 0, which is a trivial solution. Again, if you say the exponential is 0, u will be 0, another trivial solution. So for non-trivial solution, it is only the sine of lambda L that will be equal to 0. So you can write for a non, that should be none, for a non-trivial solution, it is the sine of lambda L that should be equal to 0. So that means lambda L is equals to sine inverse of 0. And you see there are so many angles whose sines are zeros. So the sine inverse of 0, there's so many of those angles. The 180 degrees, 360, etc. Those are angles whose sines are zeros. So we can talk of n pi, where pi is 180 degrees and n is equals to 1, 2, 3, etc. up to infinity, all the way up to infinity. So there will be also these lambdas, there will be so many of those lambdas. Now, remember these lambdas are called the eigenvalues. So we can make it the subject. So from here, we get lambda n is equals to n pi over L. These are the eigenvalues. Eigenvalues. Now that's what we have. So we go back to our equation here, this one, and then we substitute those lambdas. So there will be so many eigenfunctions corresponding to those eigenvalues. So you say therefore, the corresponding eigenfunctions are given by u subscript n of xt being equal to, there will be so many of these constants b, so we talk of b subscript n exponential negative alpha lambda n squared t times sine of lambda n x. And if you replace the lambda n because you have found it, that will be equal to Bn exponential negative alpha. This is n pi over L squared t times sine n pi over L x. Now, those are the corresponding eigenfunctions. Now, what is our solution, general solution? So you can say, hence, our solution, which is u of xt, is now the sum from n is equals to 1 to infinity of those eigenfunctions, u subscript n of x, t. When you add all the eigenfunctions, you get your solution, which is u of xt. So this one here is called the principle of superposition. Principle of superposition. That's what we use, that when you combine the eigenfunctions, when you add all of them, you get your solution, your general solution. So this can now be written as the sum from n is equals to 1 to infinity of b subscript n exponential negative alpha times n pi over L, this is supposed to be squared t, times sine n pi over L x. Remember, on the left we have u of xt. Now, the last step is to apply the initial condition. Apply the initial condition. So what was the initial condition? That is the condition when time t is equals to 0, and that solution was f of x. So we are told u of x0 is equals to f of x. That means in this equation, this one that I have ticked, you need to substitute t is equals to 0 so that your solution u should be equal to f of x. So we are going to get f of x is equals to the sum from n is equals to 1 to infinity b subscript n. Now remember t is equals to 0, so that will be exponential 0. So anything raised to 0 is 1. So that will be 1, which I don't need to write. Then the sine n pi over L x. That's what we have. Look at what I've written in black. This is a series. This one here is a series. And which type of series is this one? Is a half-range Fourier sine series. So you can talk of this as half-range, that should be hyphen, half-range Fourier sine series. Half-range Fourier sine series. So how do we find the Fourier coefficient Bn? Bn, B subscript n here, is called the Fourier coefficient. So how do we find them? So the Fourier coefficient B subscript n is given by the integral, or simply 2 over L times the integral from 0 to L of f of x times sine n pi over L x dx. That's how to find, excuse me, that's how to find the Fourier coefficient b subscript n. So now we know that. Now we go back to our solution u of xt. Look at this equation that I've ticked in red, this one. I'm going to replace b subscript n, and so that will be our particular solution. So I'm going to replace it here in this equation to get the particular solution. So that equation will now become, when you say hence, our particular solution is now u of xt is equals to, it is the sum from n is equals to 1 to infinity. Remember, n is a natural number all the way from 1 to infinity. B subscript n, we have found 2 over L, the integral from 0 to L of f of x times sine n pi over L x dx. That is B subscript n, so I can put this in bracket. Then we are multiplying that by exponential negative alpha, let me write, times exponential negative alpha times n pi over L, this is squared, t, then the sine. This should be sine n pi over L x. N pi, so we write this, n pi over L x. So that's what we have as our particular solution for the case where k is negative. We also need to see what you're going to get when k is 0. So we'll write here case 2. Case 2 is the case where k is equals to 0. Go back to equation star. So we are going to go back to equation star and see what you are. So let me take you back to equation star, and we substitute k is equals to 0. That's the second case. Our equation star, which one was it? It was this one. Look at that. T prime over alpha t is equals to x double prime over x, which is equals to k. And in this case, k is equals to 0. So with 0, what are we going to get? So let me take you down. Here. So now this is what you're going to get. We're going to have t prime over alpha t is equals to x double prime over x, which is equals to k, which is 0. Again, from here you can form two sets of ODEs. T prime over alpha t is equals to 0, and x double prime over x is equals to 0. This is a set of two ODEs. Set of ODEs. So let's solve them. This will be our first equation, and this is our second equation. We start by solving the first equation. So we'll write here equation 1, equation Roman 1. It is t prime, let me use another color. t prime over alpha t is equals to 0. And when you cross multiply, you get t prime is equals to 0. Remember, this is the same as derivative with respect to t. dt is equals to 0. So integrate both sides. What are you going to get? We are going to get, you integrate both sides. Even before we integrate, remember we're integrating with respect to t. So let me rewrite it. This can be written as dt is equals to 0 dt. Then you now integrate both sides. So we are going to get t is equals to a constant of integration. Call it C1. What about the other equation? Equation 2. In equation 2, this is what we have. X double prime over x is equals to 0. If you cross multiply, you get x double prime is equals to 0. So this one integrate twice. Remember, this could be written in terms of the d operator. D squared operating on x is equals to 0, where d is the derivative with respect to x. So our auxiliary equation, or simply you could write x, make x the subject. From here, x, this should be an arrow, is equals to d raised to negative 2 operating on 0. D raised to negative 2, that means is an integral operator. So you are going to integrate 0 twice with respect to x. So when you integrate with respect to x, that will give you d raised to negative 1 of a constant, call it C2. When you integrate 0, you get a constant. Then again, you also integrate 0 to give you, you also integrate that constant to give you C2 of x, C2 times x plus another constant C3. So that's our solution. And so therefore, the general solution, therefore, our general solution, which is u of xt, remember it was x times t. And this is equals to x, we have found C2, x plus C3 times our t, which was C1. And when you open the bracket, you can write this as a times x plus b. And what I'm calling a here is simply C1 times C2. And what I'm calling b is C1 times C3. They are arbitrary constants. So it means our solution is ax times b. Our solution, u of xt is equals to a times x plus b, where a and b are arbitrary constants. So this is our general solution. Now we need to apply the boundary conditions so that we know the values of a and b. Let's start by applying the first condition. Apply this boundary condition that u at 0t should be equal to 0. So what do we get? When you put x is equals to 0, you need to get u is equals to 0. So this will give us 0 is equals to b, because x is equals to 0. So 0 is equals to b. The a will disappear because it is a times 0, which is 0. So when b is 0, what will be our solution? So you can say, therefore, u of xt, u of xt is equal to A times X. Apply the other condition. Apply this condition. The other condition, the second boundary condition, that U of LT, that should also give us 0. So you put, you need to substitute where there is X, you put L in this equation, and where there is U, you are going to substitute 0. So again, this will give us, when we substitute X is equals to L, we're going to get 0 is equals to A times L. But note that L is not equal to 0. So from here, A will automatically be equal to 0 because L is not equal to 0. Since L is not equal to 0. So what do we get with that substitution? So you are going to say hence our U of xt will be A times X, which is 0 times X, that will be 0. So what we have found here is called a trivial solution. Trivial means the result is 0. So this is trivial solution. So you realize that, let me write trivial solution. What do we realize? That the case where k is equals to 0 leads to a trivial solution. And finally, the third case where k is positive. So we'll write case 3. Case 3. And in this case, k is positive. So k greater than 0. We are going to put k is equals to lambda squared. Now it is positive, not negative. K is positive lambda squared, where lambda is a non-zero real number. Lambda is a non-zero real number. So what are we going to get? Look at equation star. Our equation set is up there. So let me write here that equation star will now become equation star. It should be star. Equation star will become. So we are going to say that t prime over alpha t is equals to x double prime over x, and this is equals to lambda squared. Again, from here you can get a set of ODEs. From here you can get two ODEs. T prime over alpha t is equals to lambda squared, and x double prime over x is equals to lambda squared. We have two equations to solve. So these ones are a system or a set of two ODEs. Set of ODEs. That's what we have. Now, let's call this equation Roman 1. This other one Roman 2. So let's solve the first one. We start with equation 1. Question 1. So in equation 1, we have t prime. Let me cross multiply. That is t prime is equals to alpha times lambda squared t, which you can also write as t prime minus alpha lambda squared t is equals to 0. And you could also write this in terms of the d operator. This is the same as d minus alpha lambda squared operating on t to give us 0. Remember here, our d is derivative with respect to t. And so our auxiliary equation is d minus alpha times lambda squared is equals to 0. When you make d the subject, you'll get 1 root. D is equals to alpha times lambda squared. So the solution, I don't need to write so many things because already I explained how to find the roots and the solution corresponding to t. So we can write auxiliary equation. Auxiliary equation is d minus alpha times lambda squared is equals to 0. So what are the roots? It's just one root. D, just one root, d1 is equals to alpha times lambda squared. So what about the solution? So you can just say that therefore our solution t will be equal to, remember these are real roots, so we talk of C1 and arbitrary constant C1 times exponential alpha times lambda squared t. Let's solve equation Roman 2. So you write equation 2. If you cross multiply that equation 2, what are we going to get? It will be x double prime is equals to lambda squared times x, which you can also write as x double prime minus lambda squared x is equals to 0. And you can also write this in terms of the d operator. This is d squared minus lambda squared operating on x to give us 0. Our auxiliary equation is the coefficient of x equated to 0 and find the roots. So again here, auxiliary equation. Our auxiliary equation is d squared minus lambda squared is equals to 0. What about the roots? Let's make d the subject, the roots of the auxiliary equation. Remember from there, d squared is equals to lambda squared. And you can now get 2 roots when you take the square root. So you're going to get 2 roots, d1 and 2 should be equal to, the square root of lambda squared is either plus or minus lambda. that is real and distinct roots. One of them is negative lambda, another one is positive lambda. They are real and distinct. So therefore, the solution corresponding to these two roots is x is equals to a constant, call it C2, exponential lambda x plus another constant C3 exponential negative lambda x. Remember, our roots are real and distinct. And remember, lambda is not equal to 0. It's a non-zero real number. Now we know x, we know t. Let us replace that in our assumed solution where u is equals to x times t. So you can now say that our general solution, let's see what we got at t, C1, yeah, that's okay. So hence, our general solution, which is u, a function of x and t, is simply equal to the product of x and t, x capital times t capital. You multiply them, our x capital, that was C2, exponential lambda x, then plus C3, exponential negative lambda x. Now this should multiply t capital, which we got C1, exponential alpha times lambda squared times t. This you can simplify. If I multiply, take the C1 inside, so that this can now be written as, call it A exponential lambda x plus B exponential negative lambda x times exponential alpha lambda squared t. That's what we have. You can just say or u of xt is equals to this one. So let's apply the boundary condition, the first boundary condition, that is at x is equals to 0. So apply the first boundary condition. What are the conditions? That's u, let me use another color. It is u of 0t. U of 0t is equals to 0. That means you put x is equals to 0 and u is equals to 0 in this equation that I have ticked. So what will it give us? This implies that, should be double implication, that implies that 0 is equals to, remember we are substituting x is equals to 0, so what are we going to get? It will be a plus b. Because you know exponential 0 is 1. So add a plus b times exponential alpha lambda squared t. You might be asking, why do we remain with the other exponential? Because the other one is a function of t. But in this case, we are replacing only x. It is only x that is 0, not t. Take note of that. Now, for a non-trivial solution, a plus b must be equal to 0. Because we know exponential alpha lambda squared t cannot be equal to 0. So a plus b is equals to 0. So from here, we get a plus b is equals to 0. And you can make B the subject. This means B is negative A. Negative A. So in this equation, I'm going to substitute B is equals to negative A. So what are we going to get? You see now A will be common, which you can factor out. So we are going to get U of xt. A is now common, we can factor that out. A times the exponential lambda x minus exponential negative lambda x times exponential alpha times lambda squared times t. We have another boundary condition to apply. Let's apply the second boundary condition. So you write apply. Another boundary condition is when x is equals to L. So it is this, let me use another color, U of LT. That should be equal to 0. So that means you substitute x is equals to L capital into this equation to get U is equals to 0. So we are going to get 0 is equals to, I don't know A, we are replacing x, so we'll have exponential lambda L minus exponential negative lambda L times exponential alpha times lambda squared times t. Now, of course, you know, this cannot be 0. Also, this cannot be 0. Exponential lambda L minus exponential negative lambda L can never be equal to 0. Because L is not equal to 0, lambda is also not equal to 0. So therefore, it means it's only A that can be 0. So therefore, only A can be equal to 0. Why are we saying that exponential alpha times lambda squared is not equal to 0? Because we need a non-trivial solution. But again, we realize that exponential lambda L minus exponential negative lambda L cannot be equal to 0. So we remain with only A is equals to 0. Now, when I substitute into this equation, where there is A, you put 0, what are we going to get? Hence, we are now replacing A. Hence, our U of xt must now be equal to A, which is 0 times everything that we have on the right-hand side, and you are going to get 0, because as long as you're multiplying by 0, the result will be equal to 0. This one is another trivial solution. This is a trivial solution. So what do we realize from our analysis is that the two cases, case 2 and case 3, they lead to trivial solution. It is only case 1 that will give us a non-trivial solution. And so that is the solution of the given PDE. So when you are solving such kind of equations, always take note that you don't even need to show me that case 2 and case 3 will give us trivial solution. You only need to know that where there is k, you will substitute negative lambda squared. so that our solution is what we got in case 1. It is what we have it here in case 1, where u of xt was equals to the sum from n is equals to 1 to infinity of everything that we have there. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube, search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at other problems in partial differential equations. Bye-bye.